Hello students, today we are learning about the topic performance of single phase short transmission line. I am Dr. P.V. Tokar, Department of Electrical Engineering, for welcoming all my dear students for session 2 for the subject Power System 1, uh, Sanjivani College of Engineering, Kopargaon. So our today's topic is performance of single phase short transmission lines. Those who are absent for the lecture, so they can understood if they have missed this particular point, so they will understood the content. So today we'll start with this particular point. So first of all, already in the previous session, that is session number 1, we have discussed about different types of or classification of transmission lines. So for today's session we are starting with performance of single phase short transmission line. Starting with the diagram, this is the circuit diagram. So for transmission line can be represented by its equivalent circuit. So for this particular case we can see that there is resistance and inductor. So we have considered the inductive reactance of the transmission line and load L. Now in this case from the diagram we have various parameters like sending end voltage Vs, load current I is called as load current, Vs is the sending end voltage, then R is the resistance of the conductor, I is the load current, XL is the loop reactance, R we can also call it as loop resistance, VR is the receiving end voltage, cos phi R, let us consider cos phi R also, which is receiving end power factor, and it is treated as lagging. Vs already written in sending end voltage, and cos phi S sending end power factor. Now while drawing the phasor diagram, remember the basic concepts for pure resistive circuit. So if you go to the prerequisite or the previous concept from the first year, and if you remember pure resistive circuit, in this case if you consider the pure resistive circuit connected to the source, now in this case if you consider the whole vector diagram or phasor diagram for this, considering the voltage as the reference voltage, it can be shown like this. So voltage and current are in phase, right? It means that phi is equal to 0. and from that you will get unity power factor. Unity power factor. So this concept is very important to understand the performance of single phase short transmission line, and we will require some basic concepts. So if you understood, if you focusing on basic concept, then you will come to know that how this derivation is solved. Okay. Same diagram, just a minute. Same diagram, if we take current as the reference vector, so same diagram will be drawn like this. So sometimes we have taken voltage as a reference, and sometimes we have taken current as a reference. In this particular case, we must have to draw the vector diagram by considering the current as a reference vector. So I will give you another example. Another example. Let us consider one pure inductive circuit or pure inductor connected to the source, and so if you draw the vector diagram for this pure inductive circuit considering the voltage as the reference, it will look like this. So we can say that for pure inductive circuit, current lags voltage by an angle 90 degree. So current is lagging to the voltage by 90 degree considering voltage as a reference. Now if we consider current as a reference vector, so there will be some change in the diagram. So this is current vector considered as reference, and voltage will be like this. So if current is the reference vector, we have to treat for this diagram, and if voltage is taken as a reference voltage, we have reference voltage, we have to consider for the first diagram. Now coming back to the diagram, original diagram, let us consider the our main transmission line equivalent circuit diagram. So from this diagram, this is just a basic concept. So just for your understanding, I have explained this. Again we have to start from this point to this point, and for the phasor diagram I will draw for this here phasor diagram. So let us consider phasor diagram considering current as a reference vector. Consider current as reference vector. So again I will draw the diagram for understanding purpose. This was R, L, load, sending end voltage, receiving end voltage, load, this is XL, this is R and I. So if you consider the vector diagram, let us take current as a reference vector for this case like this. Now for this case, VR, draw the vector VR, then IR drop is in phase with the current, so direction of I and IR will remain same. Then we will draw IXL. So this generally for this case, if you consider the impedance triangle, it was like this: Z, R and XL. So impedance triangle for this circuit. So similarly, if you are considering the same parameter, I will draw XL, that is considering the current I into XL, and this part will be over here, and I will join these two vectors. I will get sending end voltage. So the angle between VR and I is phi r. The angle between VR and I is cos phi r. The cosine of the angle between voltage vector and current vector is power factor. Another thing we can show here, the angle between Vs, this vector is Vs, and I is phi s. So this is considered as sending end power factor. So this is my vector diagram for this particular case, and from this particular case I can write some expressions. From this triangle we can write OC. We can give the names to this particular triangle. Let us consider this part as O, this part as a C, and this part as a D, and this part as a E, this as A, and this as a B. Now considering these names, we can write for this particular diagram, OC square is equal to OD square plus DC square. OC square is equal to OD, this particular part, OD square plus DC square. OD square plus DC square. So if you consider the OC, whose value is Vs, so it will become Vs square is equal to OD is OE plus ED. So it is OE plus ED square plus from this part DB plus BC square. Now if you look at this length OE, for this case it is related with VR, so we can write VR cos phi r plus this part ED. ED is IR. Considering this length, ED will be, ED is equal to AB. ED is equal to AB. So ED and AB lengths are same. That is why ED will be AB and the length of or the AB is IR. So here I will write IR square plus DB, this part D and B. So this part can be written as VR sin phi r plus BC, it is I into XL. So therefore from this thing we can write Vs is equal to VR cos phi r plus IR square plus VR sin phi r plus I into XL square. So this is the final expression for sending end voltage. So For this, up till now we have got percentage regulation already in the previous lecture. The formula is Vs minus Vr divided by Vr into 100. Second point we have got is sending end power factor. Sending end power factor is equal to, it is OD by OC from the diagram, where OD is Vr cos phi r plus IR divided by OC is Vs. Then third parameter we have got as power delivered. Power delivered is equal to, it is Vi cos phi. In this case V is Vr, I is IR, and cos phi is cos phi r. Then we have got line losses. Line loss is basically I square r. Then we have got power sent out, that is Vr IR cos phi r plus I square r. Output power sent out Vr IR cos phi r plus I square r, and percentage transmission efficiency is equal to power delivered divided by power sent out. Power sent out. Now the power delivered is here, it is Vr IR cos phi r divided by power sent out is here, it is Vr IR cos phi r plus I square r multiplied by 100. So this is considering current as a reference. Now if you consider the diagram for voltage as a reference, we can also draw the diagram for the same way. And if you are considering for voltage as a reference, so the diagram will be voltage as a reference. So the diagram will be, this is the reference voltage Vr, then current is lagging to the voltage by an angle phi r, I and IR in phase, so that is why I into R will be in phase with this current, so the direction will be same. Then R and XL as per the previous concept. Then R plus JXL is Z, so I can write here impedance I into Z, so this will become I into XL, I into R, and now I have to connect this, so which will become Vs. So I got my points as O, then C, this will become A, B, and I can write here this angle as alpha. So from this also we can get this as a vector diagram considering voltage as a reference. So in case of complex notations, in case of complex notation, we can write here vector Vr is equal to, from the diagram, previous diagram, plus J0, vector I is equal to vector I angle minus phi r, because it is lagging in the negative direction, so can be written as I into bracket cos phi r minus j sin phi r. I can write impedance as R plus jXL because it was resistor and inductor connected in series like this. So here from the vector diagram I can write Vs is equal to vector Vr and vector I into Z. So vector Vr plus vector I into Z, the summation of vector Vr and I into Z will become Vs. So it is from the vector diagram, it is vector Vr plus I into Z vector. The value of Vr is, we have already got this value here, Vr plus J0 and plus I, we have the value of I is plus I, this value cos phi r minus j sin phi r into Z. So Z is written over here, it is R plus j XL. So this is what vector Vs, and for this we can write Vr plus IR cos phi r plus I into XL sin phi r plus j I into XL cos phi r minus IR sin phi r. Therefore Vs is equal to under root of Vr plus IR cos phi r plus I into XL sin phi r square plus I into XL cos phi r minus I into r sin phi r square. So the second term under the root is quite small and can be neglected with reasonable accuracy. Therefore approximate expression for Vs is equal to Vr plus IR cos phi r plus I into XL sin phi r. So this is the answer. So in this case some points we can consider. So approximate formula for sending end voltage is Vs is equal to Vr plus IR cos phi r plus I into XL sin phi r. This gives a fair correct results for lagging power factor, because for RL series circuit power factor is treated as lagging, and the solution in the complex notation is more presentable, is in the more presentable form. So this is this is all from my side. Thank you very much for watching this video.